Since the monotonicity property of mu is also an important property as we move further to the topics of measures, let us try to prove it here. Let's show that it's really valid for its definition itself. So let's start. Before I prove this one, let's start with the definition so that we will be guided. We have the previous video for that, but let us also write it here. Let mu be a measure defined for all sets on a certain sigma algebra, let's say omega, if A is a subset of B where both sets are element of omega, then this is what we're going to show, that the mu of A is less than or equal to the mu of B. Take note, it's a measure defined on all sets on a certain sigma algebra omega. And we don't know how the measure is being defined as long as this is its relationship. So we're going to show that here. So of course, the part of the proof will be letting the assumptions. Let mu be a measure, okay, defined for all sets on a sigma algebra omega. Okay? Then suppose we're going to introduce now sets A and B, the element of our omega, such that A is a subset of B. So the entire assumptions are already presented here, and what we're going to attack here is, or show that this is really true. Let me change the color of my pen just for the item we are going to prove. Hopefully you could arrive it here. And take note that we don't know how the mu is defined. Okay? It's not necessarily a counting measure, not a Dirac's measure, because it depends on what type of measure it would be. Okay? Now, how do we prove this using general perspective? Now, what if write B, okay, since B is the superset of A, or A is a subset of B, okay, so we can say that right being the larger set, be equal to the union of A and B minus A. Because this is how it goes. If I talk about a certain set B and A is a subset of that, that would mean A is a part of set B. In short, B, this entire red perspective, which includes the black one, is the union of your A and this donut part here, which is just actually B minus this A. Because B minus A, okay, B minus A is this donut, while A is just this one. So the union of two will just return to whatever UB is. And what's the purpose of this? It is because since, okay, hopefully this is really clear, we can write it like that. Since A and B minus A are disjoint. Are they disjoint? Yes, because they are removal, or they are separated from one another. This would mean this portion here is not a part of A. Okay, not a part. Okay, this will be the outer portion of A before it was removed. Okay, and mu, any mu is countably additive as one of its property, being the second property, which is if we have a pairwise disjoint collection of sets, so the mu we're able to, again, don't forget that the mu, I hope I will write it correct, that the union of A sub I, where I starts from 1 to infinity, is equal to the summation of mu sub mu of a sub i's. I starts from 1 to infinity. Meaning, countably additive. Okay? They are actually a sum. Okay? Mu is this mu of that is just sum of all the mu. So that's why mu is countably additive. We can say now, okay? We can say that if we take the mu of b, again, we don't know the definition of the measure mu, it's just equal to the mu of this entire expression. Okay? Because they are just equal to one another. By substitution, A union of B minus A. Take note, this is how we write B earlier, and that's correct. So they are also equal to one another. Okay? So what is this? Since again, look at this one here, the mu of the union is equal to the summation of the corresponding mu. So that would mean this is equal to the mu of your A plus the mu of your B minus A. Again, this is the second property of the measure function. The mu of the union of all A sub i's, as long as those A sub i's are disjoint, pairwise disjoint, we can simply rewrite them as summation of the individual measures of the A sub I. That's why here, the mu of the union is the summation of the individual measures. So hopefully you're following that. And what is the purpose of this? Okay? Since the measure of B minus A is greater than or equal to 0. This is true because our measure function is mapped to the interval 0 and positive infinity, right? So it will only take values of greater than or equal to 0. It could be 0 or it could be greater than 0. And what is the implication of that? Take note that here, okay, you will have the mu of B is equal to the mu of A plus the mu of B minus A. And since this is greater than or equal to 0, and the sum is equal to the mu of A, that would mean if this is 0, if that is 0, that would mean mu of B, okay, if, okay, is equal to just the mu of A. If the mu of B minus A is equal to 0. Okay, again, we don't know how the measure function is defined. So what if it's 0? But if the mu of B minus A is greater than 0, so that this would be true, that would mean the mu of B is greater than the mu of A. Because if this is greater than 0, a positive value, so that this would be equal, they are equal, the sum of these two is equal to just the mu of B, this should be smaller. Okay? So that if they will be added, it could match to this value. So what does this imply? We could have this relationship now based on our, okay, target here, that the measurement of your A, the mu of A, thus the mu of A is just less than, if we're going to reverse this, less than or equal, sorry for that, or equal to the mu of B. And we are able to prove the monotonicity property of your measure mu. Again, this was possible by considering that B is the union of this A, its subset, and the difference of B itself minus that same subset. So we're able to establish the relationship. Again, this is true because it's 0 to positive infinity, and that will only be its implication here. This is the proof for the monotonicity property of your measure mu. Thank you very much for watching.